Deadlocks are the true nightmare of multi-threaded code. But can they be prevented? I'm Sonia, and welcome in C++ versus Rust, where you will learn how to use asynchronous programming and deferred function execution to prevent deadlocks. Once again, welcome in C++ versus Rust. We will learn how to use asynchronous code execution in order to prevent deadlocks and also to improve performance by allowing parallel executions of the branches of our NodeGraph. In this episode, we will focus on C++ implementation and we will leave the Rust implementation for another episode. So this is our example NodeGraph, and we have learned how to create a fork in the NodeGraph so that we have two branches now. These branches could be potentially executed in parallel because they are independent. Can we achieve that by using asynchronous code execution? Let's think about it. What would need to happen? Initially, we set some value on the source node. This value gets output into the output pin of the source node. Then output pin copies this value to the connected pins. There is two connected pins, the pin of transfer node U and the pin of transfer node V. We can see that the flow from transfer node U to destination node U is parallel to the flow from transfer node V to destination node V. We will introduce deferred actions. A deferred action will be produced whenever we propagate forwards, meaning that the flow from transfer node U and flow from transfer node V will start from two independent deferred actions. These deferred actions will be produced when we propagate forwards from the output pin of the source node. Let's look at the code. This is our source node code. We can see that the process forwards method is creating a deferred action. A deferred action is a lambda. In this lambda, we lock the output pin, this output pin, and we send data from that pin. Let's see what send data does. This is the implementation of the send data of the output pin. We can see that send data takes a list of connected pins. The connected pins are the input pin of transfer node U and the input pin of transfer node V. And then, for each of those pins, we lock them for writing and set the data to our data. So we first lock the input pin of transfer node U, and we copy data from our output pin of the source node into that input pin of transfer node U. And then we unlock that input pin of transfer node U, and we lock the input pin of the transfer node V. And we repeat the process. We copy the data from the output pin of the source node to the input pin of transfer node V. After that, we unlock the input pin of transfer node V. At this stage, both nodes, transfer node U and transfer node V, have on their input pins a copy of the data from output pin from the source node. However, the input pins are no longer locked, and the output pin of the source node has finished sending the data. The next thing that we'll do will propagate forwards from the output pin of the source node, and we can see we return the value, which will be an action. The propagate forwards of the output pin will return an action. First, we transform all connected pins into a vector of action. An interesting fact is that we get a vector of action and we're supposed to return an action. We use defer parallel to turn a vector of actions into single action. We will cover defer parallel in a moment. Let's see what the transformation is doing. We call connected pin unguarded pointer getOwning node process forwards. The unguarded pointer is our means of accessing directly the pointer to the connected pin without locking that pin. This is permitted because in order to get the owning node, we do not need to lock the pin. The owning node is a constant that never changes, so it is okay to use unguarded pointer to obtain that constant from the pin. So connected pin unguarded pointer getOwning node will effectively return to us a reference to a node where this connected pin resides. Right, at this stage we have a node of the connected pin. We can now call process forwards on that node. We can remember from the source node that the process forwards method was returning an action. We can see now that iGraph node interface is defining process forwards and process backwards method as returning action. It is an action that will be deferred for later execution. So when we call propagate forwards on the output pin, we effectively iterate over all the nodes whose input pins are connected to this output pin, and we tell those nodes to generate actions for processing forwards. Those are deferred actions. So this transform into deferred actions takes a range of connected pins, applies a lambda, and as a result we get an action for each pin. So these actions is a vector of actions produced by each connected node when we call process forwards. Then we defer all those actions to be executed in parallel. They don't need to be executed in parallel, as we will learn. However, we give a hint to execution engine that they can be executed in parallel if the engine decides to do so. So we can see that the output pin of the source node is iterating over connected pins, and for each connected pin, we go to the owning node and tell that node to generate an action to propagate forwards. We go to another connected pin and to the owning node of that pin, and we tell that node to generate deferred action to propagate forwards. But this is a deferred action. We do not propagate forwards straight away. So propagate forwards at the end returns the result of calling defer parallel on the vector of actions, and that result is an action. Now we can see that it becomes a result of the deferred action that we created from source node process forwards. This means that when we call process forwards on the source node, we deferred an action that will go to the output pin of the source node, lock the input pins of the transform nodes, send the data to those pins, and ask their connected nodes to produce a propagation forwards action, and then that action is returned to the user as a deferred action. It sounds like the deferred action that we return from process forwards is returning a deferred action on its own. How does that work? Let's look at our example again. We start by loading a value using the source loader. A source loader is an interface we have queried from the source node in order to be able to load the value into the source node. We load the value into the source node. That effectively puts the value on the output pin. Next, we tell the source node to process forwards. But we know process forwards returns a deferred action. That deferred action is then passed to run actions function, which takes this deferred action and a policy. A policy is an object implementing execution policy concept. So we run the actions starting from the deferred action we received from process forwards, and we use the policy which implements execution policy concept. Let's see how run actions work. This is run actions function. There is a lot of debugging information here which helps us at runtime track down which actions were executed and what was the sequence. We can see that run actions function takes policy which implements execution policy concept, and it also takes action provided by the user. The function is called run actions, a plural, but the user provides an action, a singular. But what is an action? We can see that action is defined as optional actionable, and actionable is defined as a variant of single sequential of parallel. So we have these three types of possible deferred actions. We can see them defined here. A single deferred action is a function returning action. A sequential deferred action is a vector of actions, same as parallel deferred action. You can consider sequential and parallel to be identical, except that they have a tag value. This is important, as we will do dispatch based on those types. Our run actions is a function that has a while loop. We have an action variable, which is initially equal to user action, and then in every next iteration, it is equal to whatever the action has returned. So you can see that the deferred action returns an action. If it returns a single action, we will execute this single action, and we will continue the loop for as long as the action keeps returning an action. If the action is sequential or parallel, we will use the policy. We apply this policy to sequential action and parallel action. This is execution policy concept. It tells us that execution policy can be applied to sequential action and parallel action. Let's see what type of policy are we using in our example. We can see that the policy that we use to run our example has one Boolean parameter. We run our example twice for this policy, with this parameter being false and true. Let's see what this policy is about. This is our standard policy. It implements call operator for sequential action, and it implements call operator for parallel deferred action. For sequential deferred action, we call for each. We pass std execution sequential. It will iterate over the actions in the vector of the sequential deferred action. We remember that sequential deferred action is a vector of actions. The standard policy call operator for parallel deferred action will do the same, except it will choose execution policy parallel or sequential, depending on Boolean template parameter. So we can see if we have a parallel deferred action, we're essentially running each action from the vector of actions in parallel. We can see that parallel deferred action is a vector of actions, and each of those actions will be run in parallel. So this simple mechanism allows us to run actions sequentially or in parallel. And also we can control whether we do want to enable parallel or not. The runActions function will run the actions for as long as an action returns new action. You can see when the action is of type single, we're calling the action and it will return an action. If that action has value, action is optional, meaning that a default function may return an action or may return nothing. We can, for example, look at this deferred action from target node. It returns deferred end. A deferred end constructs no action, an optional without value. So whenever deferred action returns deferred end, this is when this while loop ends. So we will continue with the chain of actions until we see deferred end. When we see sequential deferred action, we'll run those actions sequentially in the new stack frame. When we see parallel deferred action, we'll run those actions on the new threads. However, our current thread will wait for the results before it will proceed. This means that even though the actions will run in parallel, the thread that started those actions will wait until they all finish. So we started with the source node. We got a deferred action from its output pin. This deferred action, when we execute it, it will copy data from the output pin into the input pin of this transfer node U, and it will copy data from this output pin to this transfer node V. After that, we will ask transfer node U to give us deferred actions to run to propagate forwards. And we also ask transfer node V for the same. So now we have actions from transfer node U, and we have actions from transfer node V. These two can be run in parallel because these are two independent branches of the graph. So we take those actions and we put them into defer parallel. When they execute, they will execute on two different threads. Are you curious if this code works? Let's check that. We can see the two executions here, a sequential execution and parallel execution. Remember, we're running our example for two cases, with standard policy being false, and this is sequential execution, and standard policy true. This is parallel execution. From the output, we can see that both runs resulted in the same outcome. We can see that in the first process forwards, we got values 63 and 0.777, in both cases. And in process backwards, we got 55 and 2.2, also in both cases. When we disconnected transform node V, the V path has no value in both cases. When we disconnected the output pin of the source node, both target nodes had no value in both cases. The solution works as expected, but did it run as expected in parallel? We can check that by investigating the log file. The log file will be produced if we build the debug version. We can see that the debug version also worked correctly. Let's look at the log file. This is our log file. This is where our example was run in sequential manner on single thread. I used animal names and plant names so that it is much easier to understand from which thread and from which location did this log message come from. A location can be an object or a stack frame depending on the message. This label here identifies the pin. We can see that 18 lilac is one pin that was locked and unlocked, and 13 cactus was another pin that was locked and unlocked. We can trace down why these pins were locked. Some pins were locked when we tried to read from them. We can see here the try-connect method call. It is this call. We have locked the transform U input pin for writing. This is that lock. We know that we have locked that pin before calling try-connect. So the label of the transform U input pin will be 15 squash. Whenever we see 15 squash, it is a transform node U input pin. Then we call try-connect with the source pin. That requires us to acquire another write lock on the source pin. The 23 ballet is the source pin. The cool thing about this lock is that I'm using brackets. If I now match the closing bracket, I will see everything that happened under that lock. We can see that under the lock of our input pin of transform node V, we also locked the output pin of the source node. And we here unlocked that pin. We unlocked the output pin of the source node, and then we unlocked the input pin of the transform node. In between those locks, we connect input pin to the output, output to the input, and to close the loop, we once again call input pin connect to output pin, which will simply exit. We can see the pattern repeats for another pair of pins. And if we look into the code, it is indeed another pair of pins transform node V input pin connected to source pin. And we'll see it 2 more times. This and this. Here, for convenience, I'm printing the names of the pins so that we don't have to be guessing them. So we can see that the source output pin is 23 ballet. Note that I'm just using the fact that if I print a message and I pass an entity address, I'll automatically get generated ID. So when I do this debug ID, source pin unguarded pointer, source pin unguarded pointer gets turned into 23 ballet. It's clever, isn't it? Instead of printing hexadecimal memory address, I'm printing 23 ballet, which is much easier to comprehend. And I'm printing the text into the log source output. And this is some clever trick to tell me what label will source output pin map to, and the other pins as well. You might have noticed that all those labels, the names of animals for the threads and the names of plants for the entities, they're all the same length. I tell you the secret, it would be very difficult for me to try to find such names of animals and plants that they all have same lengths. So I asked Google Gemini for help. I asked Google Gemini, hey, can you find me names of animals and plants? I would like them to be all the same lengths, and I would like 10 of each. And Google Gemini came up with the names of length 6. And I found that very helpful. So now we have mapped the names of the pins to the labels. We can use that later on when we investigate this log file. So the next thing that happens in the example is source loader load a value. So we need to log the output pin of the source node in order to write new value to it. we know that source output pin is 23 barley. And we can see here that we have locked 23 barley and we have also unlocked it. The operation of setting the data is not printed here. The next operation on the source node is to call process forwards. Coincidentally, our label for the source node is also barley. However, we prefixed it with a different number. I use those additional numbers to prevent name collision. We can see that the source node output pin is 23 barley and source node is 29 barley. Now we can see 20 grapes. What is 20 grapes? It's none of the pins and it's not a node. It is a label of the stack frame. Whenever we add some stack frame, we give it a name. This is a stack frame in which deferred actions will execute. We remember that process forward is returning a deferred action. This is the source node, and this is the deferred action that it returns when we call source process forwards. We execute then this deferred action by using run actions. And we know that run actions will loop for as long as the action is returning a new action to be run. So this is where we started execution of a deferred action. We can find the matching bracket. As we can see, in order to complete this one deferred action, we have executed some nested actions. And we can see that those nested actions have been executed on different stack frames. Let's track down what the action was doing. The first thing we do in our deferred action is to acquire a read log on the source node output pin. This is the read log on the source node output pin. 23 barley is our source output. The next thing we do, we call send data on that pin. And send data will iterate over connected pins, and one by one it will acquire a write log on the connected pin. We can see in the log we have acquired a log on 15 squash, which is transform U input pin. And we have unlocked it straight away, because we don't log what happens inside of set data, but it will set the data into that pin. The next thing that we'll do, we'll continue with the next iteration. So we will acquire the write log on the next connected pin, which we can see here. We're acquiring the log on 38 lilacs. 38 lilacs is transform V input pin. Alright, at this stage we sent the data. And now we're calling propagate forwards on the source node output pin, which we know transforms connected pins by asking each owning node of these connected pins to process forwards and return deferred actions. In the log, we'll see transform process forwards messages from the transform nodes. This is transform node. This is process forwards method of the transform node, and it also returns an action. It is a deferred action, and at the end we unlock 23 barley, which is a source output pin. This unlock happens because the guard constructed inside of this lambda is now destructed at the end of scope. At this stage, run actions has finished with one single action. We know that because we see single curly closing bracket. Let's match that bracket. This is our deferred action in action. This is what we have done in the first deferred action. However, this deferred action has returned a new action, and we can see that run actions will now use this new action. If this new action is not empty, we'll proceed with the dispatch. What was the action that we returned from here? The action that we returned from that deferred action is this transform node's deferred action for process forwards. The first thing that happens in this action is to lock the input pin of the transform node. We can see that this next action gets immediately executed. Let's match this bracket. We can see that the scope of this deferred action is quite broad. Let's see what happens inside of this deferred action. First, we lock the input pin of the transform node for reading. It happens here. But what did this deferred action return? It returned deferred parallel of the actions. We can see that deferred parallel is returning parallel deferred action, which is a vector of actions. This means that the next action that will execute is a parallel deferred action. We can see the scope of parallel deferred action is quite broad. However, we know it consists of number of actions inside. Let's see how is it executed. We know that our example is using standard policy, and in the first run we use sequential execution. The enable parallel is false. When we apply call operator to parallel deferred action, we execute this branch of this const conditional expression, and this branch will iterate over the actions and run them one after another. However, for each action in the vector, it will call run actions. This is our parallel deferred action. And this is the first action in the vector of this parallel deferred action. We see the block is enclosed in double curly bracket. It means that we're entering the new stack frame for run actions. Everything here happens in the new stack frame. This is the first action inside of this nested action. Each transfer node, when asked to process forwards, return an action, and now we have a vector of 2 actions. When we execute those actions, each action internally has some code, and this code executes on separate stack frame. The first thing that happens in this deferred action of this transfer node is to acquire a read lock on the input pin. And we can see this is the read lock that has been acquired, and it has been acquired to read the data from the input pin. We can confirm that this is the case because we can see getDataMessage. The getDataMessage is logged just before calling getData. The next message we'll see is sendData. This is sendDataMessage. And we call sendData private method of the transfer node. The sendData private method of transfer node acquires a write lock of the output pin. The process forwards of this transfer node has produced a deferred action, and this deferred action has locked the input pin in order to read data from the input. This data is read into current stack frame. After that, we release this lock. The next thing, we acquire the lock on the output pin of the transfer node. We can see that the argument to send data is a result of applying a function in this transfer node to the data that we received from the input pin. We apply a function to the data that we have received on the input pin, and the result we want to send to the output pin. This is the result of applying this function. We have acquired the write lock on the output pin. We want to set data on the output pin using this result. We set the data on the output pin. While holding the lock on the output pin, we call sendData. Let's check the actions in the debug log. We can see that we have acquired 18 lilacs. 18 lilacs is an output pin of the transfer mu node. But we can also see that we acquired a lock on 23 cactus. 23 cactus is an input pin of the target node U. Where did this lock come from? As you remember, when we call sendData on the output pin, we iterate over connected pins, and we lock the connected pin for writing. We lock this pin for writing, and that is because we want to send this data into this pin. So at this stage we have both pins locked. We can see it here, both pins are locked. And then here we can see that both pins are unlocked. The locked is managed by readWriteLockGuard, which will automatically unlock the lock once the scope has ended. The operation of setting data is not shown here. It happens between these two lines, while both locks are acquired and before they are released. The next message we see is propagate. The propagate log message is printed by this deferred action just before we call propagate forwards on the output pin of our transfer node. We first log that pin for reading. The reason we need to log this pin for reading is because we are accessing connected pins. We must prevent any other thread from changing the connections. Propagate forwards returns an action. We're propagating forwards on the input pin of the target node. We have logged the output pin of the transfer node, and now we're propagating forwards to the connected pin, which is an input pin of the destination target node. And we ask this node to process forwards, and that will give us a deferred action that we will execute once those locks are gone. When we leave the scope of current deferred action, all the locks are gone, and the new deferred action will handle the destination target node. However, we can see that the target node's process forwards returns an empty action. This means that the processing will finish here. So when we propagated forwards from this output pin of the transfer node, we have locked that output pin. We told the target node to process forwards, which we know resulted in no action, and then we unlock the output pin of the transfer node. And this is where our deferred action ends. The next deferred action is an empty action. We can see that run actions for the empty action does not run any action. When we call transform into deferred actions, we didn't filter out the actions that are empty. As a result, the actions vector had an empty action, and we returned this vector with an empty action as a deferred action for parallel execution. This could be optimized. Our defer parallel could filter out the actions so that only actions that are not empty are in the vector. And if all actions in the vector are empty, perhaps defer parallel shall return an empty action. There is a room for improvement for sure. And this is where run actions in the stack frame 35 tulips ends. This is the set of actions that were executed in 35 tulips. We can see there is another set of actions that are also executed in 35 tulips frame. The reason this stack frame has the same label is just because the way stack works. When we exited 35 tulips stack frame, it was some address in memory. And now we're entering a new stack frame, but it will be stack frame starting at the same address of memory. Let me just show you what I mean. Let's imagine this bucket is a stack. This is one stack frame. And when in this stack frame we call a function, a new stack frame is used on top of this stack frame. And when we call another function from this stack frame, another stack frame is created on top of that stack frame. However, when we exit this function, we destroy this stack frame and we return here. But then if we're running a loop and we call again the same function with new parameters, we go back to the same stack frame because memory is linear and this address in memory is the same address of memory because we're calling the same function with a different parameter. So the size of the stack frame will be the same. So we have to allocate the same size of memory on top of previous stack frame. So it will be identical between function calls. So if we call a function inside of a loop, every single invocation of this function will use exactly same stack frame. This is potentially dangerous because some of the data in this stack frame from the previous call of the function, when we exited this stack frame and when we come back with a new function call, this data is now invalid, but it looks like it's valid because no one has changed it. You had some value there in the previous iteration, and in this new iteration, you might be thinking that there is a value there, and it's not, because it's an old value. It's possible. We need to be careful with that. That is why you shall always initialize your variables. Alright, so here we're re-entering the 35 tulips stack frame. And this deferred function will be executed in the same stack frame as the previous deferred function. We use our standard policy with sequential execution. That is why those stack frames are the same. In a moment, I will show you what happens when we run in parallel. This is parallel execution, and we see the messages are in the same sequence as the last time. This is because everything happens on the same thread, which is labeled here 21monkey. But this will change. Here we load the value into the source node. We lock the output pin of the source node, we load the value, and then we unlock the output pin of the source node. We call process forwards on the source node, and that will give us a deferred action. It will be parallel deferred action produced by the output pin of the source node. In this run, we use our standard policy in the parallel mode. Let's look closely at the name of the thread column. We can see that some log messages come from a different thread. The main thread is called 21monkey, and the other thread is 25lemurs. The standard library decided to run two threads when we called std for each with std execution parallel. This must have been the most suitable number of threads for this task. There were two actions deferred for execution in parallel. It will be quite difficult for us to track down what is happening in this log file, so it is probably much easier to copy this and paste and filter by the name of a thread to see what each thread is doing. in separate views. I will leave this exercise to the viewer. Alright, so what we have learned so far? We have learned that now we have quite asynchronous code. So you can see that this approach of creating deferred actions that return deferred actions, the deferred action that's returned by deferred action is a continuation of the action. And this approach allows us to write fully asynchronous code. This example of deferred action is just a single deferred action that returns more actions that come from a different function call. However, this is a different deferred action, which is deferred sequential, meaning that this deferred action will finish first, and then this deferred action will continue. However, this deferred action will have some nested actions. Those nested actions will be executed after this action is processed, but before this action is started. You can treat this return statement from deferred action as await. You can probably rewrite this code using asynchronous constructs in other programming languages that allow you to use await. C++ also have recently introduced coroutines, which allows you to await. We will look into that in some future episodes. In this episode, you can learn how lambda expressions returning other lambda expressions can be used to create asynchronous code without using any additional language support. The code that you get in return isn't so bad. Additionally, as a user of this solution, you have full control of how these deferred actions are executed. In this example, we use standard policy, which uses standard library parallel execution mechanism. However, in the next episodes, we'll provide more sophisticated execution policy. We will try to use unbounded and bounded queues, as well as, wait for it, ultra low latency ring buffer that I have designed. Stay tuned to see that. It's coming. In this episode, you have learned how to use deferred actions, essentially lambda functions, returning other lambda functions, to achieve asynchronous code execution in a controlled manner. How does the asynchronous execution prevent deadlocks? Let's look into that. Let's imagine we want to execute this NodeGraph synchronously. This means that we load the value into the source node, which will lock output pin and put the value on the output pin, and return the control to the user. The next thing that user will do is to call process forwards on the source node. That will lock the output pin for reading to get the connected pins. And then it would iterate over those pins. It would start with the input pin of transfer node U, and then it will tell that node to process forwards, and the process repeats. So we lock the output pin of the transfer node U, and then we get the connected pin, and then we lock the input pin of the target node, and we tell the target node to process forwards. And we're holding all those pins locked because it's a synchronous call. None of those methods that we called so far have exited. So if we're calling process forwards while holding the lock, we're still holding that lock. And we don't need to hold the lock on this pin while telling this node to process forwards. That's where deferred actions come to the rescue. With deferred actions, we load the value into the source node. That will lock the output pin and set the value on the output pin. Next, the user calls process forwards on the source node. This will lock the output pin of the source node, and we will get the connected pins. The connected pin will be locked for writing, and we copy the value from source node output pin to transfer node input pin. And when we finish, we remove this lock, and then we lock for writing the input pin of the other transfer node, and we write the new value. And after that, we release the locks. And next we iterate over those input pins of those transform nodes again, but this time we don't need to lock them, because we only want a reference to an owning node from those pins. And that reference will never change. We call propagate forwards on those nodes. We get deferred action from transfer node U, and we get deferred action from transfer node V. And we put those actions into a vector, and we turn this vector into parallel deferred action. At this stage, user has this parallel action with two actions inside, but nothing is locked in the NodeGraph. The first deferred action comes from transform node U, process forwards. And the second action comes from transform node V's, process forwards. So now when we execute those actions in parallel, we will have multiple threads executing those actions. And thread number 1 will proceed by locking output pin of transform node U, and thread number 2 will proceed by locking output pin of transform node V. They are independent, and they will continue by finding connected pin and asking owning node to produce more deferred action. Notice that those pins are not locked. In this case, thread number 1 only locked those 2 pins, and thread number 2 locked those 2 pins. So we reduced the contention on the locks, and we reduced the chances of the deadlock. If we're locking those pins always in the same order, we will never get a deadlock. If we're processing forwards, we will always lock output pin first and input pin second, output pin first, input pin second. Okay? So if the order of locking is always the same, we never get into a deadlock. However, there is one known issue with the current design, and it is that if we process backwards on some thread and some other thread we process forwards, we risk a deadlock because processing backwards will first lock the input pin of the node and then the output pin of the node. It is exactly the opposite order. And if by any chance these two threads meet on any of those pins, there will be a deadlock. Chances of this occurring aren't so high, however, one is to be cautious. This problem can be solved by using lock sets. We can put both pins into a set and lock a set instead of just each pin individually. That could be something we would explore in another episode. But very clear advantage of using deferred action design is that now we can run the branches of this graph in parallel. The benefit of this design is that parallel execution happens automatically. We don't need to manually start a thread to process this branch. We have an execution policy which will do it for us. It will either start a new thread or use a thread pool. We can implement our own execution policy now that will use different strategy. But this is optional, and with current design we get parallelism out of the box, without any additional need to start any threads. Alright, so we have learned by using deferred actions we can now execute our node graph in parallel, and also we can reduce the chances of deadlocks. If we always process our graph in one direction, we shall not see any deadlocks. However, we have a known issue here that we may address in future episodes. When we process a graph in two different directions in parallel, we may encounter a deadlock. Comment, like, subscribe, and stay tuned for more episodes. Thank you for watching.